Hey folks, today we're going to talk about electric current. And the short of it is electric current is the flow of charge through something. But first we need a little bit of review. Charge. Okay, so we talked about charge in our last mini unit. And charge is the number of electrons or protons. So I'll use a little E minus and a P plus for that. It's electrons and protons. The basic unit for charge, the letter we use for charge is a Q. Okay, and that's just quantity, because really all you're doing is counting how many electrons you have compared to protons. So if you got more electrons or protons, you're negative. If you got fewer electrons and protons, you're positive. If you have an equal number of electrons and protons, you're neutral. Okay. The unit for charge is called the coulomb. Now this I don't think we talked about in our last unit. So the unit for charge is a coulomb, or just simply a C. Okay, so that is the unit that we measure charge in. And a coulomb of charge is actually a lot of charge. Okay, one electron or one proton is only equal to 1.6 times 10 to the negative 19th coulombs. Okay. If you flip that around, 1 coulomb is equal to 6.25 times 10 to the 18th electrons or protons. And by the way, electrons and protons have the same amount of charge, just one's a minus, one's a plus. So that's a lot of coulombs, or that's a lot of electrons in 1 coulomb. Now, just for example, let's say you have a 100-watt light bulb on in your house, and you turn it on for 10 minutes. Okay. Well, if you turn that light bulb on for 10 minutes, 500 coulombs are going to pass through that light bulb, which would be this number times 500, okay, which would be approximately 3 times 10 to the 20th electrons travel through that light bulb in that 10 minutes. So it's a crazy number of electrons moving through stuff when we plug them in, okay? Now, when we talk about current, electric current, that is the flow of that charge. Okay, it's the flow of charge through something. And there is an equation that we're going to talk about in a moment. But first, I want to talk conceptually about that flow of charge. Okay, so there's something called real current. And what really flows through circuits are electrons. Okay, they are allowed to move around outside of the atoms because they're hovering around the outside of the atoms. So in real life, electrons flow through a circuit. However, in most of the circuits we're going to talk about, we're going to pretend that positive charges flow. That's called conventional current. So we pretend that positives flow. Now, it is called conventional current. There's a long story behind that, but the short of it is, way back in Ben Franklin's time, Ben Franklin was one of the first to imagine electric current as a fluid, but he did not know about electrons back then. And so what Franklin said was that when an object has too much of the electrical fluid, he called it positive, positive being too full. And when it has too little of the electric fluid, he called that negative, for like deficient. Well, it turns out that the fluid he really was referring to was electrons, and it's kind of the opposite of what he said, right? If you have too many electrons in something, it's really negatively charged. So because Ben Franklin kind of thought of it as positive things flowing, that's the convention that we've always talked about since his time, and we've never changed it. Even though we know better now, we still often pretend that it's always positives moving. Turns out it doesn't matter. If you look at real current, let's say you got 2 buckets and they are neutral. So I got 2 buckets, here they are. And I have a real current. Let's say I have electrons moving from the left bucket to the right bucket. Well, what's going to happen is the left bucket will eventually have a positive charge and the right bucket will have a negative charge. Okay. However, if you talk to an electrician or an electrical engineer or even a physicist, okay, oftentimes will pretend, check this out, will pretend that pluses move the opposite way. That's conventional. Well, what would happen if positives moved from the right bucket to the left bucket? Well, the left bucket will still end up with a positive charge, and the right bucket will still end up with a negative charge, and it doesn't matter. Okay, so you can think of current as electrons flowing in one direction or positives flowing in the other. And for virtually every problem that we're going to do from here on out, we're going to use conventional current. We're going to pretend it's positive charges flowing. It's also somewhat easier to think about that way. What's the equation? Oh, I almost forgot something important. When you draw a circuit, when you imagine a circuit, like let's say here's a battery, okay, and this is going to be on your worksheet number 1. Battery has a plus and minus side. What is the net charge in a battery? Well, it's 0, okay? When you buy a battery, it's not like attracting or repelling stuff, right? It's the net charge in a battery is 0, okay? Just like if you buy a water pump from the store, like let's say a fish aquarium pump, or you buy a sub pump from Home Depot or something, pump don't come with water in it, right? It's just a pump, okay? That's what a battery is basically like. It's a pump, okay? Now, let's say you got yourself a light bulb. There's a light bulb, okay? Right now, current wouldn't flow. But when you make a path, okay, and again, I'm going to pretend it's positives flowing, all the positives in the circuit, well, not all of them, but many of them begin flowing all at the same time, okay? So if you could see this, it would look something like this. Now, this is going to be the flow of electrons first, so we'll play with that first. So notice that the battery itself, it's not, you're not adding electrons to the circuit. The electrons are already in the circuit, right? When you hit the switch, they all start moving together at the same time. Now, again, we're going to think of this more as conventional current, so this would be like positives flowing now. But again, they all start flowing at the same time. It's not like stuff spills out of the battery. It's you close a switch and boom, everything's moving at the same time, okay? Now, what's the equation for current? Okay, well, current, the symbol for current is an I. And I'm not even sure why we use an I, but we use an I. The equation for current is change in charge over time. How much charge flowed through a point over a certain amount of time. The units, well, charge is in coulombs and time is in seconds. So you could say coulombs per second, but we call that an amp, named after ampere. Okay, or you can just use a capital A. So current is measured in amps. Okay. Now, depending on what you're trying to figure out, you can leave the equation like this. You can multiply both sides by T, so your change in charge would be I times T, okay? So it's a pretty straightforward equation. I will do one example in a sec here. Before I do that example, though, currents in your house might be in the amp range. So like a light bulb will be between, a couple tenths of an amp to up to an amp. Hair dryer would be several amps. But like in your calculators and cell phones and stuff, currents are much smaller. They're in the milliamp range. You're going to be using this on a couple of your practice problems. 1 amp is equal to 1,000 milliamps. So when we use this equation here, we got to make sure that our units are always amps. So for instance, let's say you had a calculator and I told you that the current in the calculator was 75 milliamps. Well, you would need to know how many amps that is. Well, you convert that by doing the following. 75 milliamps times 1 amp is 1,000 milliamps. Cancel the milliamps out. Now you got amps. And this would be 0.075 amps. And that is what you would use for your current in this equation. Okay, you got to make sure your current's always in amps. All right. So here's my one example problem. Okay, that it will be like near the end of your worksheet. Okay, there we go. All right, so let's say you turn a light bulb on, and let's say the light bulb in your house, let's say the light bulb uses a current of 0.80 amps. And let's say you leave that light bulb on for 5 minutes. Okay. What I want to know is how much total charge flowed through that light bulb. And I want to know it in both coulombs, how many coulombs flowed through the light bulb, and also how many electrons flowed through that light bulb in that 5 minutes. Now, having said that, one other thing I'll mention in this equation here, the charge in this equation is always in coulombs. You have to make sure the time is always in seconds, and then your current will always be in amps. So when you use that equation, you got to have coulombs, seconds, and amps. Okay, so I gave you a current in amps. I gave you a time, but it wasn't in minutes, or it wasn't in seconds, was it? It was in minutes. So the first thing you got to do is figure out, well, how many seconds are 5 minutes? Well, you take that times 60 seconds in 1 minute, and that would be 300 seconds. So that's our time. The charge that flows through that light bulb in 5 minutes is going to be I times T, which is 0.8. And now our time is correct. That's 300. And you get 240. And we have seconds and amps, so our charge will be coulombs. Okay, so that's how many coulombs flow through the light bulb. Now, how many electrons was that? So then you take that number, 240 coulombs, and we know that 1 electron is 1.6 times 10 to the negative 19th coulombs. Your coulombs cancel out. In your calculator, when you divide by this, I would strongly urge you to put this in parentheses so your calculator doesn't mess this up for you, okay? All right, when you divide those numbers, you get a very big number. You get 1.5 times 10 to the 21st electrons travel through that light bulb in that 5 minutes. So keep this in mind. Here's what that is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. This is how many electrons flow through a light bulb in 5 minutes in your house. All right, so we are talking about moving a lot of electrons around. Okay. All right. I hope you found that video helpful, and thank you very much.